Hello everyone. Welcome to our paper titled Learning Hierarchical Relationships for Object-Goal Navigation. The task we consider here can be formally defined as enabling an embodied agent to navigate through the environment in search of an object of specific category using only visual features. This can be seen in the figure below, where the agent can see a snippet of what looks like a kitchen, and using only this information, it has to navigate to the toaster. The general pipeline for existing approaches include aggregating sensory input into a meaningful state and then deploying it to a reinforcement learning framework. The implicit assumption is that the robot can learn the navigation problem merely through recursive trials. However, there are three issues with this. First, the holistic scene encoder can be quite noisy due to clutter in the environment. Second, the algorithms are overly dependent on learning through trial and error, and thus cannot generalize across domains. Finally, most of these methods do not utilize prior knowledge about object relationships, something we humans consider implicitly. In this work, we present MJOLNIR. The key features of our approach are, first, we utilize hierarchical object-to-object relationship information. Second, we show that by jointly reasoning about multiple objects in the environment, the noisy scene encoder problem can be overcome. Finally, we show that shaping the agent reward can help to correctly associate the prior memory with the current observation. As shown in the image below, once the agent can correctly associate the stove with a toaster, it can easily navigate to it. Here we show the overall architecture of our model. There are three main components. First, the observation stream, where we use an object detector to find the identity and spatial location of objects within a scene. Second, the CGN stream, which associates the prior knowledge with the current observation. Third, the policy network, which correctly interprets the current state and predicts the next set of actions. Let's take a closer look at the CGN stream. The input to this network is a prior knowledge embedding in the form of a graph. We combine this information with a current observation using a context matrix and learn a common embedding through a graph convolution network. This constitutes the joint embedding as seen in the previous slide. To further motivate the agent to learn this association, we adopt a new reward shaping mechanism as shown below. We encourage the agent to learn about parent objects as well, and so provide a small but positive reward for it. For additional details regarding the context matrix and reward shaping mechanism, we refer the reader to our paper.
We use photorealistic simulator AI24 as our training and testing environment. The simulator contains 4 different room layouts, and each contains 30 different rooms, resulting in 120 rooms in total. For each layout, we use 20 rooms for training and the remaining 10 for evaluation. Our results show that our model outperforms other models in both success rate and success weighted by path length. We also evaluated on a per room basis, which showed that it performs particularly well for bathrooms and kitchens, where the object relationships hold stronger. Here we show a visual demo of our model. The target object for the agent is a vase in the living room. The left video uses a scene prior model, which does not reason about inter-object dependency. As we can see here, the robot misses the vase and keeps exploring more of the environment. In contrast, our model on the right uses the table as the parent object of the vase. So once it identifies the table, it can learn to associate with a vase and successfully detects it. In conclusion, our work demonstrates that understanding hierarchical object relationships helps with visual navigation tasks. Also, the use of prior knowledge enables us to do contextualized object search. And finally, reward shaping part motivates the agent to learn the closeness between larger and smaller objects. For additional details, please visit our website that contains more videos. We also make our code publicly available. Please feel free to contact us if you have additional questions. Thank you.